topic. Now, the thing about forces is they are measured in the Newton, and there are really two different sorts. We have contact forces and non-contact forces. So contact forces are where you have two surfaces in contact. So we're talking about friction, air resistance or drag. You've got the tension, which is maybe when something is being pulled, like a spring. And then normal contact force, I'll come on to in a little bit of time. Non-contact forces, they can act over a distance. So we might talk about the gravitational attraction between two masses. Maybe if you've got a negative and a positively charged object, you've got some electrostatic force or the magnetic force as well. Now, the thing about forces is that these are vectors. And a vector is something that has size and direction. And what that means is we can then represent a force with an arrow, where the length of the arrow tells you about the size of the force, and the way the arrow pointing is telling you about the direction. That's different to a scalar quantity, which only has size. Now, something that often causes confusion is the difference between mass and weight. And weight is a force, and that's caused by the mass of an object in a gravitational field. So like I said, we always measure our weight in newtons, we measure our mass in kilograms, and that means that the gravitational field strength is measured in newtons per kilogram. And this field strength really depends about which object we're considering. On the moon, for example, it's about 1.6 newtons per kilogram. On Earth, it's about 9.8 newtons per kilogram. So if you need to convert from kilograms into newtons, you just multiply by 9.8. Now, in order to actually measure the weight of an object, what we can use is a Newton meter. Whereas I suppose, strictly speaking, if you want to look at the mass of an object, we should use a mass balance. And that would then give you a value, often in grams or kilograms. And you've got to remember as well that the weight of an object, this acts at the centre of mass. Now, the thing about forces is that if we have an object, which I've just got here, and maybe there's a 5 Newton force acting to the left and a 10 Newton force acting to the right, what we can do is we can replace both of these arrows with a single arrow to show the overall force acting on the object. Now, if you've got 10 Newtons that way and 5 Newtons that way, that means overall there's going to be a 5 Newton force acting to the right. And this is what we call the resultant force. And this is really useful if we think about real objects. Perhaps we just have an apple which is just sat on the desk here. At the moment it's not moving, and that means there's going to be a balanced overall force. What we can do is we can maybe draw a diagram of the same thing. So this is my apple, and what we might find is that there's a force acting down. In this case it would be the weight of the object. And then there's another force which is an equal size arrow but in the opposite direction. And this one here fits this is now the force of the desk pushing back. And that's what we call our normal contact force. Now, if we had another object which maybe had a force in this direction and a force down here, we can again look at the overall force. And what we can do then is add up these two vectors together. And effectively, if I just put in a line like this, the resultant force of these two arrows, because there's one to the right and one which is down, is going to be to the right and down. So this again is another way of showing that resultant force. And because it's a vector, we're also often interested in the angle that force is acting in. So it's not just the size of the resultant force, it's also the direction that it's acting in. Something we can do which is similar to this is maybe we had a force acting at a certain angle. I'm going to call that theta. We can also resolve this force into its vertical and horizontal components. So if there's a force which is acting up and to the right, effectively there's a size of a force acting upwards and a certain size of force acting to the right. And we can see again how the length of the arrow to the right is the same as the size of how much that arrow there goes to the right. Hopefully that makes sense. I will have some more videos that explain this in a little bit more detail. But drawing diagrams is a really useful way of maybe looking at all the forces on the object, finding out the resultant force, and then finding the size and the direction of that resultant force. Now, the other thing about forces is if we have an object and we apply a force to it over a certain distance, we're then doing work. So this thing here, work, is quite an important concept. And if you want to look at the work done on an object, I'm going to call that W, so this is the work done, that's equal to the force applied multiplied by the distance that it goes. So in the case of moving this Lego block, we need to think about how far it's travelled in the direction of the force and the size of the force. Now, work done and energy transferred are both measured in joules, we've got our force measured in newtons and our displacement, the distance that it travels in the direction of the force, is measured in meters. And this then gives us the definition of what 1 joule is. So 1 joule is the work done when a force of 1 newton causes a displacement of 1 meter. The next thing we're going to look at is forces and elasticity. And basically this might be when you're bending, you're compressing or you're stretching an object, and especially the normal kind of standard spring that we have here. Now, if it's elastic, it means it goes back to its original shape when the force has been taken off. However, something which is inelastic, perhaps a spring that is bent too much, it doesn't return to its original shape, and then it's not elastic anymore. It's inelastic, or we can also call that plastic. Now for that spring, the force applied is going to be proportional to the extension of it. Extension means how much longer it's got. In fact, there's an equation that we use which says that force is equal to K times E. So again, we measure our force in newtons, our extension in meters, and this then gives what we call the spring stiffness. That has the units of newtons per meter. Now that's the amount of force required to extend something, but if you do extend something, that spring can then store some energy in the elastic potential store. And we can also look at the equation that says the elastic energy stored is equal to a half Ke squared. So this really depends on how stiff that spring is and how much it's been extended. So again, this one is a force which is measured in newtons, but this is the energy stored measured in joules. Now the next thing to consider is motion of objects. Now we've already heard that there are scalar quantities which just have size, and also vector quantities that have a size and direction. Now a good example of a scalar quantity is speed. So speed is just how quickly something is travelling. And these are just some of the speeds of everyday objects. So if you're walking along, it means that you're going at 1.5 meters per second. So every second you go another 1.5 meters. You also maybe need to think about things like the speed of sound, which is much quicker. So sound travels at 330 meters per second, depending on kind of exactly where you are in terms of the atmospheric conditions. But things like light and other electromagnetic waves, they travel at 300,000 meters per second. So even quicker than that. Now, scalar quantities also include things like distance, but there's a vector equivalent called displacement. And this includes not just the distance that something is moved, but also how far the direction that it's moved from its start point. So vectors always have a direction as well. Another vector quantity, a bit like speed, is velocity. And at GCSE, we define velocity of an object as the speed in a given direction. And we can also look at how quickly this velocity changes, which is then our acceleration. Now, looking at the relationship between distance and speed, we can say that S is equal to VT. Now, this is confusing. We don't use the letter S for speed. That's just something that we don't do. Instead, we use the letter V to represent speed or velocity, and this is measured in meters per second. S actually stands for our displacement. So think about the S for displacement, or the S in distance. So S is our distance in meters, and then time is in seconds. Now, another more useful way of looking at this equation is that V is equal to S divided by T. So the speed is equal to the distance divided by the time taken. And if you want to work out how quickly something is going, you simply need to measure the distance that something's gone and then time how long it takes to go that distance. Now, there's one little interesting thing about velocity if you're doing the physics, and that basically means that you can have something where something's velocity might be changing, but its speed stays constant. And this is where you've got something which is moving in a circle. So maybe you've got an object and it's rotating in a circle. It might be going 5 meters per second, so it might have the constant speed, but its direction is constantly changing. So sometimes it's going left, sometimes it's going down, sometimes it's going right, and then sometimes it's going up. So when you've got circular motion, this is a special case where you've got an object which has a constant speed, but a changing velocity. Now, something which it's really useful to do is to draw different graphs to represent an object which is moving. Now, one of these is called a distance time graph. So we measure our distance in meters up here, and we have our time in seconds along the bottom. And what we might then do is plot some data for an object, and we can see how its distance changes with time. Now, on this graph here, the gradient of that line is equal to how quickly the distance changes per second, and that means the gradient is equal to our speed, v. Sometimes, however, you might get a curvy line, and then in order to work out the speed of that object or the velocity of that object from this line here, what you then do is you draw a tangent to that line. Once you've drawn a tangent to that line at the point that you're interested in, you can then measure the gradient by looking at the change in y and the change in x values, so you can actually then work out the value of the speed on this curved line. Another type of graph which is really useful is the VT graph. So this is our speed in meters per second, we've got our time in seconds here, and again what we can then look at is maybe how an object's velocity changes over time. Now for this graph here, the gradient is going to be equal to the rate of change of velocity. We're looking at how quickly that velocity changes per second, and that means our gradient is then equal to our acceleration. And actually, the equation that we can use to work out the acceleration of an object is equal to the change in velocity divided by time taken. So for this, we measure our velocity in meters per second, our time in seconds, and that means our acceleration then is the amount of meters per second per second. So the units for acceleration are meters per second squared. And we can often find that from a VT graph by looking at the gradient. And if we actually look at the area under this VT graph here, the area is equal to the velocity times the time, which we saw over here, the velocity times the time is equal to the distance travelled. So under a velocity time graph, the area is equal to the displacement. Now when we look at the change in velocity, what we're really looking at is the difference between the final velocity, which is v, and the initial velocity, which is u. So we can also say that this change in velocity is equal to v minus u. But now we can actually introduce another equation which says that v squared minus u squared is equal to 2as. So this one here looks a little bit confusing. Effectively, this is our final velocity in meters per second. Take away our initial velocity in meters per second. Often this is just zero in lots of equations that you might, or questions that you might be given. A is our acceleration in meters per second squared, and then our time here is in seconds. Sorry, our distance is measured in meters. So if you get a question and you can identify what you know from the question, you can often decide which equation you can then use to work out your final answer. Now, if you had an object which starts falling, initially it's going to accelerate quite quickly and it's going to get faster and faster. Now, for the apple falling towards the ground, there's going to be a constant downwards force called weight, and this doesn't change. But its air resistance increases as this gets faster and faster. Now, there are 3 Newton's laws that you need to remember. Now, Newton's first law basically says that if there's the resultant force acting on an object is 0, so there's no resultant force in it, then stationary objects remain stationary. But things which are moving continue to move at the same velocity. So for example, if you've got a racing car which is travelling as fast as it possibly can down a nice straight road, there's going to be a point where the air resistance is equal to the thrust of the engine and it doesn't get any faster. We then have Newton's second law. Now basically this says if there is a resultant force on an object, then the object is going to accelerate. And the size of that acceleration really depends upon the mass of the object and also the force that's being applied. So we can often write this as F equals ma. Now this is just the equation form of Newton's second law. So we've got our force in newtons, our mass in kilograms, and our acceleration in meters per second squared. And again, just to say that the acceleration of an object is proportional to the resultant force in it. So you get a bigger acceleration for a bigger force. And it's inversely proportional to the mass of the object. So that means that you get a smaller acceleration when you have a bigger mass for a certain force that's been applied. And then finally, we've also got, to complete the set, Newton's third law. And this simply states that whenever 2 objects interact, the forces they exert on each other are equal and opposite. So what that means is if we have the moon, for example, and this is being attracted to the Earth at the moment, the force of the attraction of the Earth on the moon is the same as the force of attraction of the moon on the Earth. And what we then have are a force pair. So that's Newton's third law. So a way to think about this is that if the force is equal to 0, then objects which initially had no velocity stay at 0. Objects that were moving still keep moving at a constant velocity. Here, if there is a force, then that force is going to be causing an acceleration. And here, what we're saying is that if you've got an object A and an object B, the force that they exert on each other are going to be equal and opposite. And here the mass is what we often call the inertial mass. And that's basically because things which are still want to stay still and things which are moving want to stay moving. And this inertial mass is basically their resistance to wanting to change what they're doing. And if we want to define inertial mass, then we pretty much define it as the ratio of force to acceleration for an object. Now I've pretty much run out of room again, so let's continue this on the page below. So the next thing we need to look at is the stopping distance for a vehicle. Now this is basically the total distance that a vehicle travels, which includes the driver's reaction time when they're thinking about and actually reacting to something they might see ahead, and then the distance that the car then, or the vehicle then takes to stop. So this is your stopping distance. Now the thinking distance is going to be affected by things of the driver. So this might include things like tiredness, by alcohol, by drugs, both legal and illegal, and also things like distractions, including mobile phones. So that's what's going to affect how quickly the driver reacts. But once they put the brakes on, that factors that affect how their braking distance might be applied, might be changed, include the condition of the roads. So it could be something which is maybe wet or icy. We're thinking about the condition of the tyres and the brakes. And of course, these and the total stopping distance are also going to be affected by how quickly that car is going. Pretty simply, the faster you're going, the bigger the stopping distance is going to be. And if we think back to the energy topic, the reason that a vehicle is slowing down is because there's a couple of brake pads which go onto the brake inside the wheel. And what this is doing is then transferring some of the initial kinetic energy store of the car into the thermal energy store of the brakes, which get hotter, and also the surroundings, which heat up as well. Something we also look at is momentum. And momentum is simply defined as the mass times the velocity. So momentum, confusingly, has the symbol little p for momentum from the word impetus, and this is equal to mass times velocity. Now for this, we measure our mass in kilograms, our velocity in meters per second, and that means the unit for momentum are kilograms meters per second. Now this is also a vector quantity, because it really depends on the direction that you're going, and you might have maybe a positive momentum or even a negative momentum. And it's really important that you try not to get momentum confused with kinetic energy, which also depends on the mass and the velocity of an object, but that then has a unit of joules. Now, in a closed system, what we can say is that the total momentum before an event is equal to the total momentum afterwards. So what we can say is that the momentum before is equal to the momentum afterwards. And finally, that's it. We've done all of the forces topic for AQA GCSE. It's been a big one. Hopefully there's been something here which has been useful. Thanks for watching. So this is revision of the AQA waves topic. Now what waves do is that they transfer energy. And there are really two different classifications of waves. We have longitudinal and transverse. Now these longitudinal waves, what they have are the particles in the wave. These are vibrating maybe back and forwards in the same direction that the energy is being transferred. So if energy is being transferred this way, the particles are just going backwards and forwards. In a transverse wave though, the particles are going side to side and the energy is being transferred at 90 degrees. And examples of a longitudinal wave might include things like sound and ultrasound, but for a transverse wave we have the whole of the electromagnetic spectrum. So that includes things like light, and we're going to come on to that very soon, but also we have things like the water ripples on the surface of water. Now if we were to look at the position of a load of particles along a certain bit of something which is vibrating, there's a wave travelling, what we can look at is the distance of the particles from their rest position. And this distance here is what we know as the amplitude. Okay, and so amplitude is the distance between where the particle normally is and how far it vibrates up and down. There's also a distance which is one complete wave cycle, and this is known as the wavelength. And we give the wavelength the symbol lambda, which is a Greek letter, a bit like an upside down Y, and this represents our wavelength. So we define the amplitude of a wave as the maximum displacement of a point on the wave away from its undisturbed position, while the wavelength is the distance from a point on one wave to the equivalent point on the adjacent wave. So it could be peak to peak, could be trough to trough, or maybe this point to this point. Now, if we think about a wave, there's a link between how long it takes for each wave and the amount of waves per second. So the amount of waves per second is the frequency. So we can see now that there's a quicker, higher frequency here, but each wave takes less time. And what we can look then is the link between the time period for a wave and the frequency. We find that the time period of a wave is equal to 1 divided by the frequency. Now for this, we measure our time period in seconds, and it's capital T for time period, and we measure our frequency, which is the number of cycles per second, in hertz. So that frequency of a wave is the number of waves passing a point each second. The other equation that is really important to know is known as the wave speed equation, and this says that V is equal to F times lambda. So V is our wave speed. This is measured in meters per second because it's just the speed. We measure our frequency in hertz, and the wavelength, because it's a length, is measured in meters. And with this information here, it allows us to maybe look at things if we're measuring real waves. It might be as simple as we're measuring the speed of sound, where what you have is maybe two people who are a certain distance apart, and you can make a signal between these two people, and if you know the distance between them, which is S, maybe they make a signal and they record the signal that person's doing. Maybe they're clapping their hands or bursting a balloon. They can actually time the time it takes for that sound wave to get to them. And then you should remember that the speed is equal to the distance divided by time. Now you can do something similar with maybe a water wave in the tank. Maybe if you knew how the wavelength of that and you knew the frequency, you could then work out the speed of those ripples. So the electromagnetic spectrum is a whole series of waves, and all of these travel at the same speed through a vacuum. This is also the speed of light, which is 300,000 meters per second. So that's pretty quick. And there are 7 main categories of waves that we're interested in. And so we go from radio at one end through to gamma at the other. So you've got radio waves, microwaves, infrared, which means below red. Then we have visible light, and because you've got infrared and then visible, that means we start with red waves, which are the longer wavelength, and then we go Roy-Yabiv to violet light at this end of the spectrum. We then go beyond violet into the ultraviolet. We then have X-rays and then gamma rays. And gamma rays are again this thing which are emitted by the nucleus of an atom. Now basically, as we go this way through the spectrum, what we find is that the wavelength lambda decreases, but also as we go along this way, the frequency increases. And what we find is that when you have higher frequency electromagnetic waves, they're going to be more dangerous. We can say they're more ionizing. And really from this point onwards, what we have is ionizing waves. Now what that means is that ultraviolet isn't great for you, X-rays are worse, and gamma is worst of all. So that as you have a higher frequency, the waves become a little bit more dangerous. So why is it that you need to know about this? It's because these have loads of uses. For example, if we think about radio, this is used for television and radio, so used for communication. We also use microwaves for communication, and this might include things like your mobile phone, but also we have satellite communication. And we can also use this to heat up food because it causes certain molecules to vibrate at the same frequency. So we can also use this for heating up food in your homes. When it comes to infrared, we can use this for heating because infrared is just a type of heat radiation. And we can also use it for night vision, so perhaps you have cameras that can see in the dark. Visible light, used all the time, including things like fibre optic communication. So that's how you get your broadband nice and fast. We then have ultraviolet, which is used for energy efficient lamps and also for sun tanning, so if you want to get bright orange. Running out of space here a little bit. Now, X-ray and gamma, both really high frequency. These can be used for medical uses. So they can be used to actually scan the body to find out where something's gone wrong, maybe using a conventional X-ray, maybe a CT scan, or maybe some radioactive tracer. But they can also be used to actually blast away at the damaged parts of the body to actually maybe reduce cancer, for example. So here are just some uses of different parts of the electromagnetic spectrum. Now, something else that light does is it refracts. So refraction is when you have a wave and it meets a different medium, so it might be a different substance, and then it changes direction because it changes its speed. And you might get perhaps a glass block or a perspex block, and you shine a ray of light at a certain angle, and this hits the surface here, so this is my normal. What happens then is that this changes direction through the medium, and then when it comes out the other side, it then goes back into the original direction. So this is called refraction. And the reason for this is if we were to maybe zoom in on this part over here, where we had the waves hitting the surface, if we think about the wave fronts hitting that surface, one side of the wave is going to hit the surface before the other. And as it hits the surface and slows down, it does something a bit like this. So it starts to slow down on that side still moving. And then that means it all, as one, because effectively one side is slowing down before the other, it changes direction. Now that's maybe not so obvious, but if I put in this line here to show the direction of that wave, what we can see is as the wave slows down, it changes direction. Now, before we start looking at electromagnetism, let's just think about normal magnetism. So this is a bar magnet. It's got a north pole and a south pole, and there's a region surrounding this where a force acts on other magnets or maybe magnetic materials. And we can see that if we put this other magnet over here, something's going to happen, and it's the south end which is attracted to the north. So when you have unlike poles, they attract. If the two poles are the same, they repel. Now for this magnet, the strongest field is going to be at the poles. And we can actually plot this using a small plotting compass where when you put it on the table, you can see which way it lines up, and then you can actually then start to draw the field lines. But the field lines look a bit like this. So that's just a rough sketch. It's supposed to be symmetrical, and the field lines go from north to south. I'm just going to put some arrows on the diagram to show that. So this is the magnetic field around a simple bar magnet. Now this is also the shape of the magnetic field around the Earth, and this is the reason why if you have a compass, if you're navigating, it always points to north. So the evidence that we have this magnetic iron core in the centre of the Earth is because of the magnetic field that we can experience and actually detect every day. But something really happens if you have a piece of wire and you connect it into a circuit so that there's a current flowing. What we then have is what we call an induced magnet. So just by having a current flowing in a conductor, we then have a magnetic field. Now, if we have a conductor like this, which is just a wire, then if we actually start to look at the field lines, so maybe we've got the current flowing in this direction, I'm just going to draw the field lines in green. What we have are these concentric circles that get more and more widely spaced as we actually draw that. And we can actually think about the direction of this by using our right hand rule. So if this is the direction of the current with my thumb, then my fingers point in the direction that that field is going. So we have the field lines like this. So I just got an arrow to show the direction of that field. Now the thing is, if we had more wires, then we'd have a stronger magnetic field. And actually if we had it coiled round into a coil like this, we'd have an even stronger magnetic field. Now this coil of wire here, which is a coil of wire that can carry a current, is called a solenoid. And if I was to draw a solenoid a bit like this, I could then draw the magnetic field lines through it. And actually what we find is in the middle we have these lines which are really close together, like this. And they also come around the side like that. In actual fact, this is the same shape as we have around a permanent magnet over here. But in the middle we have this dense magnetic field where all the field lines are really close together. Again, these can go from north to south. And so in a solenoid, what this behaves is when you put a current through it, this behaves a bit like a bar magnet. And that's incredibly useful for all sorts of devices. Now when you have a current and it's moving, this then causes there to be a magnetic field. And these three things are really closely linked to one another. So you have a current flowing, so there's a movement of electrons inside a wire, we cause a magnetic field. But what would happen if we had a magnetic field and a current flowed in that? What you then get is the third side of the triangle, you get the movement. And this is called the motor effect. So the motor effect is put to good use in motors. What we have inside this motor here is we have some permanent magnets. When the current starts to flow, we then get movement. And we can actually use something called Fleming's left-hand rule. Now for this, my first finger tells me the direction of the magnetic field. Now a magnetic field we actually give the symbol B to. My second finger tells me the direction of conventional current, and my first finger tells me the direction of the force that a conductor is going to experience, and therefore the direction it moves. So we can see that we've got from this triangle over here, we've got magnetic field, we've got current, and then my thumb is the force or the direction of that movement. So these three things are really closely linked. Now what this means is that if you had just a single wire in a magnetic field, we could predict which way it's moving. So let's imagine we had the north end and the south end of a magnet like this. Between the two of them there's going to be a region where you have a magnetic field. I'm going to draw this in because we know that the magnetic field goes from north to south. Now this wire here is effectively coming out of the paper towards you. I've just drawn that with a dot. We can then use Fleming's left-hand rule to predict which way that wire would move. So first of all, my first finger is a magnetic field going from north to south like this. My second finger is a current, which is coming out of the paper. It's pretty awkward to do this. And my thumb is pointing up. So what we have here is the wire would move in this direction. Obviously we could turn that wire to go downwards by either reversing the direction of the magnets, or we could reverse the direction of that current. So effectively what we're doing there is if we were to reverse the direction of the magnetic field, this would happen and my thumb would point down. Really awkward to do. If you're in an exam and you see people starting to do this, there's probably a question about the motor effect and Fleming's left-hand rule. But how does a motor work? Well, effectively what you have is you've got a coil of wire, and some of the wire is coming, some of the current flows towards you, some of that current is flowing the other way, and what you then have is as soon as you pass a current, basically the piece of wire, some of it moves up, some of it moves down, and then you can use a thing called a split ring, and that allows you to then have electric current flowing always in the same direction inside that motor. We can also use an equation to do some calculations, and we can actually look at the size of the force on that conductor, and F is equal to B/I/L, where we measure our force in newtons, we measure our magnetic field in the Tesla, like the car, current in amps, and length in meters. Now it's not just motors that use the motor effect, we can also use it in loudspeakers. Now in a loudspeaker you might have a very small circular magnet like this, okay, and this is connected to maybe a large paper or cardboard cone. Okay, so you've got your magnet at the bottom. What you then do is you have a coil of wire that comes in and it goes around this several times. Okay, now what happens is that if you have a current flowing in one direction, you've got a current flowing, you've got a magnetic field in this permanent magnet down here, and what that means is that maybe when the current flows this way, the thing here moves up. If you then have the current flowing in the other direction, it moves down. And by varying very quickly which way the current is flowing, that causes the speaker to move up and down, which then causes a load of sound waves to be radiated from this.